Hey guys, Jay Keast here, and I've got a video tutorial for you with a different kind of, not spin, because we're not spinning, but a different take on the Gaussian surface concentric sphere type problem. So let's say instead of them telling us what the charge of this inner sphere is, let's say that they tell us that it's charged to an initial potential. So they give us the initial potential of this sphere being, let's say they give it to us as just V naught. So they tell us that this sphere is charged to initial potential V naught, and let's say this outer sphere is initially uncharged. And they're both conductors. Okay, and what can we do from knowing that this sphere is charged to an initial potential? Well, potential is related to electric field, and electric field is related to charge. So what we can do with this is figure out what charge this thing will have initially. Okay, so to get that, we've got to think about electric potential and how it relates to electric field. And let's think about, this is a charged conductor. So if you think about it, all of its charge is located on that outer surface. And it's got some charge out there. I'm going to say it's got some charge Q naught. I don't know what it is, but I know it's got some charge because it's charged to an initial potential. Okay, so to figure out what this Q naught is, this charge that's on this outer surface here, we've got to think about electric potential. How does electric potential relate to charge? Well, we've got to think about how does electric potential relate to electric field. So the electric field, if I think about the electric field at that surface, the electric field, if I made my Gaussian surface be equal to or right at that surface, then I would get an electric field being equal to Q enclosed, which in this case would be Q naught, all over 4 pi, and my R would be A squared epsilon naught. Now, what would the potential be at the surface? Well, potential, remember, if we're dealing with this as if it were a point charge, then potential is just electric field times distance. But what's my distance? I've gone out to A, which means V naught is equal to my electric field times A. But if I take this and multiply it by A, this A squared cancels, leaving me with just A. So I would get a V naught being equal to Q naught over 4 pi A epsilon naught. You could then solve for Q naught, and once you knew Q naught, you could figure out, okay, well that's going to induce a negative Q naught over here and a positive Q naught out here, and you could get your electric field in terms of your electric potential. Because once you know what Q naught is, think about it like this. Q naught would be equal to V naught times 4 pi A epsilon naught. What if you took that and substituted it in here? So my electric field would then become Q naught, which is V naught times 4 pi A epsilon naught, all over 4 pi A squared epsilon naught. Yeah. My electric field would then become V naught over A at that particular surface. If I wanted to think about my electric field as a function of R, well then things would be a little different, because my electric field as a function of R would be Q naught 4 pi R squared epsilon naught. But I know that the electric potential inside this conductor is a constant. This would be the potential inside that conductor, and that would be a constant. So this Q naught would also be a constant, because each of those numbers is a constant, meaning this charge isn't going to change. So, oops, I kind of cut us off there. So, we could relate electric field to electric potential. Since this is a constant, we could substitute that in for Q enclosed. Once I got outside of this region, think about it. I've got negative Q naught here, and I've got positive Q naught out here. The electric field inside a conductor is always 0. So I know the electric field in this region, it would be 0. Once I got outside of that sphere, my Q enclosed would just be Q naught. So there would just be a lapse in the electric field. It would be electric field, electric field, electric field, no electric field, and then electric field. It would pick up as if this hadn't happened. So let's figure out what my electric field would be. Don't like that shadow being cast there. Let's figure out my electric field for R less than A. Spoiler alert, electric field would be 0. Let's figure it out for when electric field is in between A and B. In other words, the electric field inside this region. But we have to figure it out in terms of variables given. And we just figured out that Q naught is equal to V naught times 4 pi A epsilon naught. Once I'm inside that region of space between my insulating sphere and my conductor, I can use Gauss's law, and my Q enclosed is going to be Q naught. So my electric field times my area, which would be 4 pi r squared, being equal to Q enclosed, which is Q naught, which is this. Hey, look at that. I've already got the epsilon naughts canceling. And then my 4 pi's are going to cancel, leaving me with my electric field being equal to V naught times A, the inner radius of my sphere, over r squared. This would be in between the two conductors. Once I got inside this conductor, like we said, it would be 0. And then once I got outside the conductor, it would be this equation again, because my Q enclosed would just be Q naught. Because remember, this outer sphere was initially uncharged. So my electric field graph versus position, if I go A, B, C, from 0 to A, my electric field would be 0. In this region, it would be like this, 0 again, and then it would pick up right where we left off. Now, the reason it picks up right where we left off is because this outer shell was initially uncharged.